Without further ado,
Yeah. Okay. Yeah.
I'm very sorry. You know, you're right. There was a last-minute replacement, and I totally just read the wrong bio because Tomer's not here today. It's been a wonderful morning. Okay, so in that case, Tomer had a visa problem.
Yeah.
Yeah. Well, you know, a lot of that going around. All right, Udi Yavo, also of InSilo, is the CTO, and you know, so obviously we got upgraded. That's, you know, if only you could get a speaker upgrade too, or a room host upgrade as well. You'd be better off. So Udi also has tons of experience in cybersecurity. Prior to InSilo, he spearheaded the cybersecurity unit at the National Electronic Warfare Research and Simulation Center of Rayfield Advanced Defense. If you're getting the gist of this, these people have worked together for a while. And you know what? You don't want to listen to me talk, so let's just have him do it.
Yeah. Okay, so let's start. We already heard enough about that. Okay, so what we're going to talk about today is injections. So we'll start with user mode injections. We'll go really quickly through common injection techniques. Then we'll go through to quickly over power loader. It's advanced injection technique. And we'll move on to an improved version of power loader that works both on 64-bit and has other features we'll talk about. Then we'll move on to kernel injections. I'll go over common injection techniques first, and then we'll go through a new injection techniques. We call it trap frame injection, and we'll finish with codeless code injections, which I'll explain later. Okay, so let's start. So quickly, through common injection methods, probably the most common one is just you open some process, allocate some new code in.
Hello, I'm Geek here. Unfortunately, video rigs seem to freeze up and no one seemed to notice until about the 20-minute, 20-second mark in. So, unfortunately, we lost some audio up until then. Sorry about that.
It is pretty well documented, and the basic steps to using it is just to wait on load image notify routine, which gets called each time an image is mapped into the target process. Write some payload into the address space. Let's say something that calls LDL load DLL to inject some DLL or load library. There are several variations to it, but the principle is pretty much the same. And then insert APC using k insert q APC. Code for this method can be found in the internet relatively easily, so there's no need to elaborate here. Another less common method was used by Dooku. That's pretty why it's worth mentioning. It's also well documented, but I'll quickly explain how it works. Like the APC routine, it waits on the load image notify routine for the main module to load. Let's say the driver is evil driver .sys. So once the main image is loaded, the driver maps some payload into the target application. Then it replaces the entry point of the target image with a jump to the payload. And once the payload executes, it restores the original bytes on the main image entry point and jumps back to it. This is nice since it ensures that the payload will execute before the main code executed. Another method which is, to our knowledge, pretty much undocumented, is we call it import table patching. I don't think it has any formal name. So it's never been used by malware, to our knowledge as well, but it is commonly used by security vendors. Trustea, Symantec, and Microsoft AppV use it. And there can be probably very similar method that exploits the TLS, it's the thread local storage directory of the P file to achieve similar results, but I won't go through it. So this is the way it works. First, you wait on the image notify routine like the other two methods, allocate new import table for the main, for the executable, and copy the old import table with a small modification. Just add the DLL you want to inject as the first entry of the new import table, then redirect the import table of the original image to the new one. And once the injected DLL loads, it can restore the import table. What's nice about this method is, let's say you attach with OLI or immunity debugger or anything like that to a process which is injected this way, it will appear as if the DLL, the injected DLL was originally part of the process. You won't see the loading part. So quick summary of these methods. These methods are used by both malware and security vendors. All of them pretty much used to inject DLLs. And they required some kind of payload in user mode address space, maybe except for the import table patching. And pretty much all of them use the load image notify routine. So now let's move on to a new method we developed. We call it trap frame injection. So trap frames are created each time the CPU handles exceptions or interrupts. Basically what it does is to save the state of the user mode program on the kernel mode stack, so it will be able to restore it once the system call or exception or interrupt handling, whatever is done. The structure used by the kernel to all this information is a k-trap frame. There is a pointer to each thread. There's a pointer to a trap frame in the k-thread structure. What we see now is the structures, the way they're defined. There's nothing really special here. The only thing important is we can see that it pretty much holds the entire state. So everything that will be restored can be modified before it goes back to user mode. So in order to make trivial injection with this with trap frames, all we need to do is to wait on some callback routine. It could be thread creation, registry access, file access, whatever. And once the callback is triggered, allocate some payload into the target application, alter the instruction pointer that was saved in the traps frame. When the kernel goes back to user mode, the payload will run and restores normal execution when it's done. But this talk is about codeless code injection, so the idea was to do it without adding any new code to the process and still be able to do complex operations. For example, to send a post request from Internet Explorer, open remote shell from some process, and keep it something that's easy to write. So we'll be able to do complex things and without too much hassle. And the main limitation is no code injection. No, we won't add any new code to the process. So let's see how it can be done. So instead of using a RIP to alter the execution, we'll try to mess with the user stack. So once again, let's see what happens in create thread callback and use it to do something trivial. So what we can do is build some rope chain, for example, to load the library. Then alter the stack pointer to the beginning of to the start of the rope chain, and when the system call will return, the rope chain will execute. But as I said, we won't do it without adding new code. So loading a new library is kind of cheating. So we do it without loading our own library into the process. But first, we have a few challenges we have to solve in order to make this thing work. First, we need to be able to get return values back to kernel mode. So we are able to react to things that happen in user space. So the first solution, which I'll dive into later, is to use the device handle in order to get notifications. I'll explain it in a moment. Another possibility is to trigger some hookable events, such as registry access, wait for it to happen, then grab the return value for somewhere, and fix the context. This is harder to do, and we didn't go that way. Another issue is deadlocks, because we don't know the exact state of the user mode program when the callback is triggered. We can't be sure that any code we inject, a rope chain we inject into the program won't cause some kind of deadlock. Let's say load library is being called, so some lock is held right now, so we can't use it. So the solution to this was to use the dedicated thread, and we'll see how we do it later on. We get this dedicated thread. Another issue is what if we need to use a user mode function that requires a callback as parameter. So one possibility is just not to use these functions. We didn't need to use such functions for demos we did, and we still were able to do almost everything. If we had to do it, we probably use the method I mentioned earlier, and we'll trigger something that's hookable, like registry access, file access, or something like that, and then restore the context accordingly. So now let's move on to how to use anti-close function to trigger callbacks back to our driver. So what we're going to do is to use a device object. We'll file create device for the driver. And whenever we require a callback, we'll just create a new handle in the target process and build a rope chain that will eventually close that handle. Now, once the handle is closed, what's going to happen is that the IRP will be generated and the cleanup handler of our driver will be called. So what we're going to do is take I forgot to say, we first save the value we need at somewhere in user mode, so it won't be destroyed. And then when the callback is triggered, we get this value and act accordingly. One thing to note is that we can't just move, for example, AX register or IX register to some other register and then get it directly from the trap frame, because it might be lost when, let's say, it's a 32-bit application which triggers some system calls. It won't go directly to the kernel. It first go through a chain, a 64-bit row 64, and the register might be lost along the way. So now we know how to get callbacks, but we still don't know how to create a dedicated thread. So let's see the API for creating new threads. Basically, there are two arguments we care about. The first one is the procedure that the thread is about to execute, and the other is the parameter it's about to receive. So what we're going to do is we're just going to use the trick we did to get callbacks, and we'll set the create thread call with anti-close as procedure and the device handle as an argument. So what's going to happen is that when the thread just starts to execute, we'll get a callback to our driver, and now we'll be able to tell that we are in our own thread. It's a dedicated thread. No deadlocks are going to happen. And once we're done with the process, we can let the thread die, and everything will work well. Okay, what we did next is we wanted to write this kind of programs easily. So we developed a relatively simple API. Actually, we probably could have created some kind of small compiler to just translate C code to the way it should be in order to execute in our driver. We didn't have time to do it, but it is possible. So the first API is a create program. You just tell it where you want this program to run, for example, Internet Explorer. Then you add steps to the program. For example, open socket, read socket, things like that. Tell it to run with a run program, and once it's running, it will wait until the target process does something that we can hook on, and build a rope chain for creating a dedicated thread, and starts to run the program in the context of that process. There are several methods API we are using to open a library that's already loaded in the process, call some function, load a new library to the process. For example, if it's a process that doesn't have a socket API loaded into it, we might need to load it. Okay, so this is a very simple program that uses the API. We create a program to run in Internet Explorer. We add a new step to it, for example, to load some library and run it. And the code for loading some library is just do load library, add it to the rope chain, and load some DLL. So what I'm going to show right now is how this driver actually works and how it creates a reverse shell from a WinLogon process. Okay, so we have here netcat running, waiting for some connection. I'll just restore the snapshot. I didn't want to go through it during the presentation. So here we can see Process Explorer. We're gonna want to see that WinLogon indeed opens some process, and what we see. Okay, I'll make it full screen so it will be easier. See it? I hope it's visible. Okay, so what we're looking at now is this is already the driver already created the dedicated thread here, and this is the first chain that it runs on the dedicated thread. I'll now single step through it. What we did is a modified version of the driver that we made some kind of debugging support to it, so it injects breakpoint each step during the injection, so it's easier to walk through what's going on. When we do it without adding breakpoints, the debugger can't even single step through it. It just happened. So let's see what happens. Okay, so first I'm loading a sockets library. The interesting part will be when we get to ZW close, which is empty close. What's gonna happen now is that the driver is gonna get a callback because the handle is closed, and it's gonna write a new rope chain into the stack. So what's gonna happen is that the stack just jumped up, and the new function is being executed. So now it's a WSA startup. We need to call it before creating any sockets. So once again, I'll go through it. Actually, I'll just let it run and see where we go. So the next step is gonna be creating a new socket. So the same way we saw in the previous call, the chain is executed, we reach the ZW close, and a new chain will be created. Now it's for connection. I let it run. Now the same thing will happen for create process. It's just a simple reverse shell for demo purposes, but we also wrote things which are much more complex than that. Okay, so let's let it run. Okay, as we can see, a new command line was created under WinLogon. And let's see what we got on the netcat side. So where am I? So I'm system, and that's what that's the reverse shell we got from the driver. Okay, so let's go back here. Okay, so to sum things up, injections are a pretty important factor for both security vendors and malware writers. Techniques are getting much less generic and probably more advanced and actually cool. The new techniques are constantly being invented. We'll probably see new things in the future. We'll publish source code in a few days on our site, so you can go and see it over there, and that's it. If anyone else, thank you.
All right, we have